Hi guys, today we are just discussing the basics of how a automotive computer works. Wanda has just done a demonstration where we turned on can you show them there? Can you turn it on again, Wanda? Wanda's done a demonstration where we turned on a Arduino. We use the Arduino to turn on a fan. Kubi, can you bring me one of the solenoids at the back? There's gearbox solenoids here in the corner. Now, Banaya, if we look at this over here is a BMW 8 HP gearbox controller. So this gearbox controller, in order for this gearbox controller to shift gears, we have a microcontroller in there and we have a pump. So if we break it down to the very basics, we use the microcontroller. It probably works like this, where we have the microcontroller there, then we have the pump. Okay, let me just go and grab a pump. The same. So over here we have a three-phase motor, right? So that is a three-phase motor. We'll do experiment with this tomorrow or so, where we will run it. That is found in a DSG gearbox. So that motor is attached to this pump here. Then we have a solenoid. Now, what can you tell me about that solenoid there, Wanda?
The solenoid.
Yeah. Would a microcontroller be able to switch that solenoid on?
By itself, no.
No. So it would require
external power source.
It will require external power source. Okay. So let us look at this here. So we have the pump. So the pump will pump hydraulic fluid into a reservoir, or what do they call that? In the VW gearboxes, they call it a accumulator. So it will go into the accumulator, and let's say, for example, this is maybe a single speed gearbox. Now we have our pump. Then we would have our thingamajigs. There is the pipe going to the clutch. So we would have one solenoid there. So we would have one solenoid there, and then we would have our clutch over there. And let's say we have another pipe connected there, and that would be going where? To the thing to select our gears. So it's a single speed gearbox. So when that solenoid pushes there, it will probably push the gearbox into first gear. So what happens is the MCU will turn the pump on. And once the system is pressurized, the pump will turn off. Okay? So how would we turn the pump off? How would we know when to turn the pump off? We would require some sort of input. So maybe a pressure sensor. And the pressure sensor would be wired to the microcontroller, right? Now, where would these guys be wired to? Input or output? There's two here. Output. So microcontrollers have GPIOs. What is GPIOs?
General purpose input output.
General purpose input outputs. Now, that is the reason why when we start our training, we start off with the basics of computers so that you can understand it's a device that can accept input. Number two, it can store it. So what we're going to be looking at today, we're going to be looking at the storage. You guys have been spending time reading and writing EPROMs. So today we're just going to get a bit of an understanding about what more about what EPROMs are. So we're going to look at the files that we have inside the EPROMs. Okay. You wrote the key to that file, right, Vinay? So if you can open up that file, you can send one of these minions there to open up the file. Okay. Can we open up the file there? Can you show him which is the blank file and which is the file where the key is coded? You can just double click on the file. Okay, it's fine. Just go ahead. Okay. So jump in between the two files. And that is the version of this. We coded keys to one of our version files, and those version files are found in our ebook. Okay, so can you guys see where's the go to key number 1? What is different there, guys?
That file is key ID.
Okay, where is your key ID, Banai? Can you read that? Can you read that transponder? Just wire up the Tango, then read the transponder. Gabriel, go and read the transponder there. Wrong. Yeah. Yeah. Okay. Didn't you have it now? Read it, Gabriel. Where did you go to? Yeah, but okay, read it. What did it? Just read it now. Click on the flag. Okay, note the data there, minimize it. Why don't you write it down? Leonard, can you write down the key data? So it will be 0B 23 Okay, can you guys locate it? Do you know where it is? So we got it repeating 3 times. So in your key data, is it 95?
This will be 23B795.
So remember yesterday's file. We had a nibble swap. So what do we have today? Could be, right? They are byte swapped. Okay, to understand that, we're going to focus on, today we'll focus on these items here. See, at the end of this lesson, this is what I want you to remember from here. Okay, number one is offsets, because sometimes you need to understand offsets. Sometimes you will be required to modify offsets, or we would give you addresses to modify, and then you would need to understand what those addresses are. Okay, so firstly, let's go back to data storage. Now, Wanda has shown you guys transistors. What states can a transistor be? It can either be on or it can be off. Now, if we would like to represent a on or a off with a number, what number system would we use? We'd use the binary number system. So the binary number system is a base 2 number system, meaning there's two variations. It can either be 1 or it can be a 0. Good. Now, where does 1s and 0s fit in over there? Benaya? Where do you think 1s and 0s would fit in over there? In that EEPROM that we read, there are transistors. Okay. Now, in that key, in that 4C key, we also have transistors. Now, if we would want to use a group of transistors to represent a letter, for example, how would we do that?
Converting it to hex. Converting all of the data of those outputs into hexadecimal.
Yeah, on the right track there, but we need to have something to represent it. We would need to have a method to represent it. I'm not going to get into much depth about that. What we want to do is I'm going to tell you which method it is used over there, right? So on this section of our file, we have hexadecimal. And on that section of our file, we have ASCII. Okay, let's take the letter A as an example. Now I want you guys to go online and look for a ASCII table. Don't look for don't use a calculator, look for a table. Go and Google a ASCII table. And we're going to look at the letter A. Capital letter A, right? The big A. And the reason why I'm saying get a table and not a calculator, because with the table, I want you guys to get used to, if you go and look for a calculator will just give you the ASCII, it will just give you the binary equivalent. Look for ASCII to binary table. Have you guys found it? Gabriel?
Yeah.
Okay, what is the letter A in binary? So let's say we have, what is the letter A in binary?
0, 1,
0, 1, 0, 0, 0, 0, 0, 1. So if these were transistors, This one would be off, this one would be on, this one would be off, 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 and on. If we were to represent that using transistors. So how many do we have there? 1, 2, 3, 4, 5, 6, 7, 8. So that is a byte. So these are 8 bits. So each bit is a transistor. Each bit will be represented by one transistor. Okay. Now, when we have it in our file there, you can go back there. If we look at our file there, it's not in bits, it is in hexadecimal. So what I want you guys to do is I want you now to go and find a binary to, or get a hexadecimal to ASCII converter. Not a converter, get a table, don't get a converter. Get a hex to ASCII. A lot of guys might find this boring, but we try to emphasize this in the beginning. You need to understand this. Sometimes you will run into certain vehicles like VWs, whereby the component security will be 7 bytes as an example. Certain VWs will have 7 bytes, or sometimes we would half of the, like in certain vehicles, like some VWs where the cluster, once we do VW coding, you look at the cluster on a 4th EMO system, some of the bytes are missing in the ECU. So when we speak of that, you guys need to understand what we mean when we say that some of the component security bytes is missing in the ECU, but you'll find a full set of bytes in the cluster. Okay. Some vehicles will have component security that has 16 bytes. Or if somebody tells you to enter the first 4 bytes, you need to know what to do there. And once, if you would like to get to know this a bit more, you can start learning about microcontrollers and see how the microcontrollers address, go and look at certain addresses to find information. And you would also understand things like checksums. If we look at, we received another ECU, Junior. That Audi ECU has got the Audi ECU that you were busy with yesterday. Yeah, it has a checksum fault where? Inside the external flash, there's a checksum fault in there. So your EEPROM was good, your internal flash was good, but you had a checksum failure in your external flash. This is where this knowledge is applied. Okay, we're going to get to checksums a bit later, but firstly, we need to just understand this, what is happening there. So did you guys get the converter or the table? So what would the letter, capital letter in A be in hexadecimal? What would it be?
1010.
In hexadecimal, 1010 is not it. 41. So in hexadecimal, the letter A is equal to 41. You understand? So if we go here and we type, if we go here on the hexadecimal side and we type 41, we get the letter A in the ASCII section. Do you understand that? So this side here is the same thing on this side here. It's just that on this side here, it is in hexadecimal, and this side it is in ASCII. Okay. Now, the reason why we imagine if that was in hexadecimal, imagine that was in binary, how many lines would we need? We would need a lot. So that is why it is we represent it in hexadecimal. Okay, so we understand this now. So the hexadecimal is a number system. You guys need to go and read up a bit more on the hexadecimal number system. So the hexadecimal number system, it starts off, if you look there, it starts off from 0. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, B, C, D, E, F. Okay. Now, okay, so we know that. Okay. We sorted there. We understand what hexadecimal is. We know what ASCII is. You guys can go and read up about ASCII. Tonight you can go and spend some time reading up about ASCII. We know what a byte is. Do we know what a byte is? Everybody know what a byte is? Okay, so we know what a byte is. So we have 8 bits in a byte, right?
Oh, sorry.
And then next, so we know what a byte is. Our next one is a nibble. Okay, so there is 4 bits in a nibble. Okay, now I was working on a Mercedes-Benz truck. We have a problem with the Mercedes-Benz truck where a fault code is generated because the truck is detecting tampering in the engine control unit. Now, as I was busy looking at that, I could identify where the keys are because the keys are also mirrored in the box. So the keys will be mirrored 3 times. That is also for redundancy. If something goes wrong, it will be mirrored in a different location. Okay, so that is what mirroring means when it comes to that type of thing there. So we're happy there. We're happy for today there. We understand that. Okay, we're going to go a step further now. We skipped one, offsets. You need to understand what offsets are. Now, if we look, Gabriel, can you just go to B7? B7. Not the offset. Click on B7 there. So B7, that B7 there is stored in, we look there, it is offset 0. So let's go to that 69 there. So what offset is that 69 stored in? 0BA. 0BA. So that will be, that address is 0BA. Now, why is that important? Why is this an important skill here? The reason why this is an important skill, let's say for example, you need to turn a immobilizer off in a 2 kD